Welcome, everyone. We frequently talk about the many benefits of cloud computing, like on-demand capacity, automatic scaling, consistent security controls, and managed services that remove undifferentiated heavy lifting. But one of the less visible benefits of running on AWS is the fact that our teams constantly obsess about resilience in our services and in your applications. At AWS, we serve millions of customers across 37 regions, handling billions of requests a second. This scale provides us with unique opportunities to innovate and make investments that most companies couldn't justify in their own data centers or applications. It also requires us to dive deep on a myriad of details that others might overlook or that many businesses wouldn't bother with. Resilience is more critical than ever for you, our customers, to deliver essential services across the globe that power economies, governments, critical infrastructure, and more. And after over 7 years of working here at AWS, I've come to learn that we think a little bit differently about resilience. That's summed up really well in this quote. We're really proud of AWS's operating record, and we hear feedback routinely from customers that when they moved to the AWS cloud, their reliability improved significantly. But we still occasionally have incidents, and to some degree, they're inevitable. Our obsession with resilience means that we are continuously trying to learn and improve from every incident so that we'll have fewer future incidents and that they'll be shorter and smaller, affecting fewer customers. We're aiming as an organization to be anti-fragile so that after each incident, we're better than we were before. And there's a lot of innovation that goes on to achieve this. Some of the innovation includes delivering transparent improvements in our services that are mostly invisible to customers. Other innovations seek to reduce the amount of work customers have on their side of a shared responsibility model, letting AWS shoulder more of that burden for you so that you have less to do. My name is Mike Aiken. I'm a Senior Principal Solutions Architect, and I support customers across AWS build and operate resilient workloads in the cloud.
And my name is Gavin McCullough. I'm a Senior Principal Engineer in the AWS Resilience Organization. We own a set of products like Route 53 and Application Recovery Controller, as well as working across AWS on resilience initiatives. I also work as an AWS call leader, which is our equivalent of an incident commander, if that term is familiar. So today we want to pull back the curtain a little and share some of the behind-the-scenes innovation that helps make AWS the best place to run mission-critical workloads and build for adversity. Before we get into too many details, I want to talk a little bit about how we think about operations at AWS. We consider operational excellence to be a centrally important part of being an engineer, an engineering manager, or for that matter, a leader. Our role guidelines talk about it. It's part of all of our performance and promotion discussions, and it's a key part of what we all do. Our developers don't just write the code, they carry pagers. That's done deliberately, so they are thinking carefully all the time about how the service is going to operate in production. We need our developer teams to truly own their customer experience, whether that's the way the service works, the semantics of the APIs, or the availability and performance of the service. Service teams all run their own regular weekly ops meetings where they review recent incidents, look at tickets, examine their metrics dashboards for anomalies, and plan how to improve the operational state of the services they own. The common example conversations you'd hear would be like, look at that graph. The P99 latency of that API call has gone up by 10 milliseconds since Tuesday. What happened? We obsess about little details like that. We have very high expectations for engineers diving deep. It's not about just resolving issues, but understanding why they occurred so we can improve. As with any software services, AWS services have issues occasionally. Most are pretty innocuous, with most customers not even noticing. But we have to take even the small issues seriously. Obviously, our top priority is always to mitigate any customer impact immediately. But our next priority is to learn. We want to analyze these events, learn the right lessons, take the action items, so that we don't just correct a specific issue or bug, but make the system more resilient for future unexpected events. Finally, we aim to share what we learn across teams. Our org at this stage has thousands of developer teams. We want to share the learnings, mental models, and best practices so that all of our teams can learn from each other. This is really where we start to achieve the anti-fragility that Mike is talking about. As AWS and Amazon have grown, one of the challenges has been working out how to succinctly communicate our core operating ideals across a large organization. And so to help with that in recent years, we've been working on what we call availability axioms. These are a set of concise best practices that our service teams all follow and expect of each other. So having these short axioms gives us a common language in which to discuss our systems. Let's look at a few examples. The first is region isolation. We expect AWS regions to operate highly independently. So in the rare case that a problem occurs in region A, we know it will be limited to region A and will not affect any other region. This very simple principle has major availability benefits for customers. As we now have 37 regions and growing, it's critical that each region operates as independently as possible. Our second axiom relates to availability zones. For those of you not familiar, AWS regions are all built with 3 or more availability zones for redundancy. These are physically separated groups of data centers spread around a metropolitan area. They have separate, independent power and networking. Every AWS region is designed to gracefully handle one availability zone being impaired, or in the rarest case, even completely unavailable. So with that in mind, our AZ resilience axiom says that every regional AWS service must be able to tolerate an impairment to one AZ without degrading their customer experience. We push teams hard to meet this, and we test it pretty frequently. An important third axiom is centered around testing. That code should be tested prior to going into production, won't be new to anyone. But the axiom goes into quite specific details on best practices around unit testing, integration, acceptance tests, things like that, and what we consider to be best practice. In addition, teams also have regular use of chaos testing and what we call game days, which I'll talk about a little more later on. And the last axiom is around overload protection. We've learned a lot over the years about protecting systems against overload and the many ways overload can arise. People tend to imagine at first that overload is caused by bad actors, and that can happen, but in practice we often find overload is caused by how systems interact with each other in unexpected ways. And so our systems all have to be built to defend themselves against overload from all of their callers. As with people, it's critically important that our systems have mechanisms to quickly and cheaply say no when asked to do more work than they're going to be successful at. And as with people, deciding who to say no to is also really important. So let's explore a set of recent examples in which AWS has been innovating to deliver on these 4 availability axioms.
We're first going to take a look at how we improve the regional isolation of AWS services and customer workloads by exploring the evolution of the security token service over the past 14 years. STS allows a given IAM role or user to assume a different role temporarily, usually to perform some task with different privileges. It's kind of like the sudo command on a Unix system, except with one really important difference. STS is aimed at assuming purpose-built, least privilege IAM roles. The mechanics are that when you call STS with the assume role API, it returns a temporary set of API credentials for the IAM role that you're assuming. These credentials are short-term and typically expire in an hour. And so STS is used in many different ways. For example, single sign-on systems, or when you authorize an AWS service to take an action on your behalf. When we launched STS in 2011, long-term credentials and users were pretty standard across the industry. STS's use of short-term credentials and restricted roles was a significant innovation at the time. And this approach may seem obvious now, but back then, this was a genuine invention. We were exploring new territory, and we were still learning about how the service was going to be used by customers. And it quickly became apparent how powerful and important STS was going to be. As its popularity grew, so did its critical nature within the AWS ecosystem, and more workflows started to make use of this API. Because STS was distributing credentials for IAM roles, we decided to locate the STS endpoint in the same place as IAM, in US East 1. Both of these were considered global services, meaning that there was a single endpoint that users and services in all regions used to call its APIs. This seemed like a minor detail at the time, but as we learned more about this new service and how it was going to be used, we started to realize this wasn't really the optimal choice for STS. And so while we originally thought of STS and IAM as being strongly coupled siblings, there were actually some very real differences in how the services were used operationally. First, IAM is globally consistent. We replicate all of your roles and policies to every enabled region so that everything has the same view of your IAM resources. And this requires a central source of truth that's managed by that global endpoint. In contrast, STS is local and stateless. Tokens, once they're produced, aren't stored by AWS. The same token also can't be retrieved twice. So there's no similar need for a central source of truth and global consistency. Second, the IAM APIs are typically used only during IAM resource creation and updates. This normally happens at build time, when you're deploying things through CloudFormation stacks or releasing things through a pipeline. STS, on the other hand, is used frequently during runtime. Obtaining temporary credentials from STS was becoming part of the critical workflow for applications and temporary access in AWS. And a lot of AWS services start depending on STS in ways that they wouldn't for IAM. This also means that STS is called much more frequently than the IAM APIs are. So as we looked at these two services, we began to realize one of these isn't like the other.
So the question we started to ask ourselves about STS was, given how important it's becoming for AWS services and for customers, could we make STS regional in order to provide the strict regional independence we want from all our services? So we started work in 2014 to deliver regional isolation for STS. And this was a pretty big decision for the company, as it's going to be a lot of investment, but it was the right thing to do for both AWS and for customers. So by early 2015, STS has launched regional endpoints in every region globally, and AWS is now encouraging customers to use them over the global endpoint. And as time passes, we see most customers adopting the regional endpoints, and things are going pretty well, but slowly over time, it starts to become clear that not everything is migrating. In September last year, we did a deep dive into this question. Although regional STS had been available for nearly a decade, a significant set of you were still using the global STS endpoint and not getting the benefits of the regional isolation that we wanted. We realized that we needed to change our approach to get where we wanted to be. We had made the APIs available, we had recommended them strongly in documentation and blogged about them and all the things we could, but we weren't getting the transition we wanted. And the fundamental problem we realized was that for a lot of customers, migration to regional APIs required them to take action. And it had become clear that at the scale of our customer base, that wasn't going to get us there quickly enough.
So you can see the global STS API here running in US East 1, and the other 16 enabled by default regions around the world that people were calling it from. So let's zoom in on North America a bit, and we can see what's happening a little more clearly. So even for the workloads, right, in all these other regions, customers are regularly making calls back to US East 1 to get their short-lived credentials from the STS Global Endpoint. Obtaining those credentials was introducing a cross-region dependency. and it didn't provide the regional isolation that we wanted workloads to have. Now, this is how we want things to actually work. Requests originating from each region for STS credentials should be answered locally in that region. We don't want requests to the global endpoint to actually go to US East 1 anymore. So a workload in US West 2, when it calls the STS Global Endpoint, should be answered in US West 2. And the same for every other region across the globe. This would ideally create the regional isolation we want in STS without customers in those regions having to do anything to get it. But this kind of change can be complex. We really needed to understand the customer requirements to make the change with near-perfect transparency. So here's what we did.
So as you can imagine, one of the biggest challenges in running cloud services is figuring out how to make big changes while no customers notice. Our goal here is for near-perfect transparency. So let's look at some of the requirements and what we did to meet them. The core of what we're trying to do here is that every customer get their STS calls answered in their local region without them needing to know or make any changes. The first thing we did was to build out 16 perfect replicas of the global service, one in each additional region, so with 17 region endpoints in total. The regional service looks slightly different to the global one from the perspective of clients, so we couldn't just transparently reroute everyone to the regional endpoints. We decided that for now, the simplest thing to do was to actually build and run a global endpoint in every region. It's worth noting that as opt-in regions already enforced use of regional STS, we didn't have the problem there, so we didn't need to do it in those regions. When we spoke with the identity experts, they asked us to ensure that the change was made in such a way that we would only ever answer clients in the same region. So for example, global STS requests before we started were answered, if they were made in Sydney, would have been answered in Virginia. We wanted to answer those requests locally in Sydney, but never to route them to any other region. And requests that originate outside an AWS region would continue to go to US East 1 as before, so nobody gets any surprises in terms of where their requests are being handled. And to achieve this, we used an integration with Route 53 Resolver, the DNS resolver in your VPC. When you query sts.amazonaws.com now in those VPCs, it transparently returns you the IPs of the new in-region endpoints. We made this change very carefully, one AZ at a time in each region, and monitored to make sure all the customer workloads were continuing to work as normal. One of the other more subtle aspects we had to think about was CloudTrail logs. Every time you make a call to STS, an audit log is delivered to CloudTrail. Most AWS customers configure global CloudTrail logs so that all of their logs are globally delivered to a single region they choose. But for customers who don't, CloudTrail logs are generally emitted in the region where the service is running. And as global STS was running up to now in US East 1, its logs were being emitted in US East 1. We're going to change which region it's running in. So we needed to be careful that even while we answer that STS request in, say, Sydney, we must ensure the log still shows up in US East 1 as normal, or customers may notice the change. And to ensure we're being very open about this and transparent, we also added an extra line of metadata into the CloudTrail log, so you can see in which region we actually answered the request. Over the longer term, our goal is to eventually deprecate this global endpoint. This project is about accelerating the benefits, getting you that really early, while we slowly work on the deprecation. The newer AWS SDKs were all already defaulting to the to the regional STS endpoint. But we realized that a sizable portion of customers were using older major versions of the SDKs, and they were defaulting to the global endpoint. So as part of the long-term strategy, we're also updating all supported SDKs, even the older ones, to ensure they default to the regional endpoint. Now that's going to take a few years to take its full effect because people pick up SDK changes at varying rates. We said near perfect transparency because it's not going to be perfectly transparent. There was at least one case where we figured it wouldn't matter. So a request that gets answered, that originates in in Sydney up to now, would have taken a sizable portion of time going to Virginia and back. And when we start answering it in Sydney, it's going to be answered much faster. But we were pretty confident that most customers would be comfortable with that.
So in April of this year, we publicly announced that this work had been completed. STS has deployed a dedicated STS Global Endpoint in every enabled by default region and rerouted traffic to it within those regions from your VPCs. So now that it's done, what was the effect? As the work proceeded through this project, the STS team tracked the number of unique accounts that were seen making cross-region calls back to the STS Global Endpoint in US East 1. So in order to show this, we've normalized it as a percentage of the total callers on the y-axis. So as you can see, as the project starts, we're oscillating below 100%, and as the project proceeds, from about mid-March to about mid-April, this number drops down practically to 0. Many thousands of accounts, which were dependent on cross-region calls to STS, are now being answered locally. They're getting this update and this benefit with no changes made on their part.
I mentioned before that the other nice side effect of this was going to be in terms of latency of calls to STS. As obsessive operators, the STS team already had monitoring on the performance of calls to global STS from every region. So as calls previously had to transit from places like Singapore and Sydney to North Virginia, the latency of responses tended to be dominated by the network round trip time. You can see the STS team's measurements of latency change as the project proceeds. It was really satisfying to see calls of up to 230 milliseconds dropping dramatically. By the end, every default region now consistently sees responses in under 20 milliseconds. You've got to keep in mind that there are millions of calls going to STS every second that are benefiting from this. So it's a really big change. So the first availability axiom was ensuring our regions operate independently. And focusing on this axiom drove a major change to ensure that all customers of STS have their calls answered in region, even those customers still calling the global STS endpoint. And so this has significantly improved both the reliability and performance of STS for everyone.
The next axiom that we want to talk about is how we're making our services and customer workloads more resilient to AZ impairments and gray failures. To see what we've done here, we need to spend a little bit of time talking about a service called AWS Lambda. Like STS, Lambda has become a critical service to both our customers and our own services. I remember when I was a customer and AWS Lambda launched in 2014. Back then, I was kind of a newbie on AWS, and I didn't really understand how or why to use it. I was still humming along on EC2 instances. But if we fast forward now over a decade later, AWS Lambda has become a core compute primitive for event-driven architectures. I use it in almost everything that I build. It's a core component of a number of AWS services and runs mission-critical workloads for customers. But to get to that point, we've had to innovate a lot to make it resilient. Lambda operates at a massive scale. Their fleets often have tens of thousands of nodes in them. And these are the fleets where we run your Lambda code. And like everywhere else in AWS, we really care about your customer experience. It's our top priority. This makes managing the health of these fleets critical to the experience that Lambda delivers. But occasionally, there can be one single instance that becomes impaired. It doesn't always outright fail. Maybe it starts misbehaving, becoming a little slower, or producing more errors than the rest. And when you have just one bad node in a fleet of 10,000, it could reduce the availability of that fleet to 99.99%. And Lambda's availability goals are actually much more aggressive than this. These bad nodes that are limping along, not completely failed, can also be really hard to find. And that can make recovery really difficult and require manual intervention. And we wanted Lambda to be more resilient when these types of gray failures occur. Automated detection and recovery is essential to maintaining really high availability numbers. So to do this, we needed to change our approach to fleet health observability.
So especially with big services like Lambda, one of the things we've learned is that, as one customer put it in a blog some years ago, your nines are not my nines. A single node in a fleet of 10,000 experiencing faults might, as Mike says, only drop the service's availability by 1/100%, if you consider it as a single aggregate number. But that doesn't always capture the real customer experience. What may be happening in practice is that most customers have perfect availability, and a small number have less. So if you as a customer happen to be unlucky and that single bad node is hosting many of your Lambda invocations, you could be having a worse time. So this is why it is so important that we obsess over even that one instance in 10,000. We need to detect and remediate this very fast. And when these kind of situations occur, you might think, well, we just need better health checks, right? It's simple. And when a host fails unambiguously, as in just stops answering completely, dies, whatever, a simple shallow health check works great. When a host is down or stops responding, we can detect it and remove it easily. And if the host is actually down, you're not going to make the situation worse by automatically removing it. But the scenario we're dealing with here is what we call a gray failure. The host is still answering. It's doing so slowly, intermittently, or with unusually high error rates, depending on how we've defined this. And the health state of the host is sort of kind of ambiguous. In particular, there's a risk here. If we remove a lot of gray failing nodes that are actually answering customers at the same time, we could make the situation worse. So one approach is to employ deep health checks that examine the host application more stringently to identify these gray failures. In doing this, however, we have to be careful not to set ourselves up for an overreaction. The hosts are still doing some good work. Automatically removing a large number of hosts might turn a mild event into actually a more severe one. And this leaves us with kind of a hard decision. How deep can my health checks safely be? Turns out this is a really difficult question to answer. So when we're dealing with gray failures, simple binary health checks are really hard to get right. What we've learned is that health checks in gray failure scenarios need to be budgeted, so we limit how much we're willing to take out automatically. And they need to be non-binary comparisons. No host is ever truly perfect. So we need to rank and remove the worst host only. So looking more closely at this topic of budgeting, suppose to deal with gray failures, we say any instance is unhealthy if its error rate exceeds some number. And in this context, let's say we choose 4,000. And maybe these hosts all have some shared dependency. And maybe someday that dependency has a problem. Now all the hosts start failing at high rates. They may still be doing some useful work, so we wouldn't want to take them out because we'll take them all out. So we have to have a budget. Maybe it's okay to take 10 or 20% of them out, maybe 30%, but we can't take them all out. I mentioned also that it's a non-binary comparison. You can see pretty clearly in this picture that the yellow instance is very different. It is an outlier relative to the rest. And that's not really based, as a human looking, that's not based on there being some magic threshold we chose. It's because you can see it's an outlier. That's why you would take that out. So this is what we need to build into our systems. We're looking effectively for the needle in the haystack. We want to find a single instance with problems while the others are fine. So how do we do that in practice? How can we compare metrics like errors among a pool of tens of thousands of nodes?
In AWS services, we send structured log files to Cloudatch logs, typically using our embedded metric format. That allows us to combine logging and metrics into a single pane of glass. And because we have metric data in our log files, we can analyze that data using Cloudatch Contributor Insights. Contributor Insights actually started as an internal AWS monitoring tool that we made available to customers as well. If you were to ask our service teams, you'd probably find that Contributor Insights is one of their favorite features of Cloudatch. And that's because at our scale, it helps us understand individual customer experiences without needing to have an individual customer metric. Right? So way more cost efficient and allows us to focus on just the top n number of contributors. And Contributor Insights allows us to look at very high cardinality data. And that means that when there are a lot of unique keys, like instance IDs, and it allows us then to graph the top n contributors to some data point from those log files. And it produces visualizations like this. So now we have a method to visually detect when there's an outlier for error count in a fleet of thousands of nodes. But we really want to do more than visualize this, right? We want to take action on it, and we want to do that with automation. So in AWS Lambda, we built a fleet health service. We have our worker nodes here on the left, and they send in their log files to CloudWatch logs. And you can see this example log file here includes data like fault count and the instance ID. Then we analyze that data with Contributor Insights rules. And in this case, we're looking at individual instance contributors to fault count. Next, we can create a CloudWatch metric math alarm on those rules. In this rule, we're looking for any contributor that's responsible for 66% of the total errors the service is seeing. What we found is that large percentages like this work pretty well. They're fairly conservative, which means they're not going to produce a lot of false positives. But even a large value, like 60 to 70%, will reliably find unhealthy instances. Once the alarm is triggered, a worker node responds. So the first thing it does is find that top contributor's ID. Then it's going to check its token bucket. And this is a really important step. We don't want automation like this to run away due to some bug or an unforeseen condition. So there's a velocity control on how many times the health service can do this within a defined period of time. So after we ensure that there's enough capacity within our token bucket, if the unhealthy instance is part of an auto-scaling group, we'll call the setInstanceHealth API and let auto-scaling do its thing. Otherwise, this worker node terminates the unhealthy instance and lets the service that owns it control replacing it. And so this is a service that started as something Lambda built, but has actually become a general purpose health service that lots of AWS services take advantage of. It's an example of how a lot of innovation comes to be at AWS. An individual team, or even a single engineer, has a great idea, and they build something that's useful for lots of different teams. And it ends up making us all more resilient. Another challenge that we saw in Lambda were gray failures affecting single availability zones. And this happens when some event impacts the latency or availability of resources in that zone. And while we run your Lambda invocations across multiple AZs, even a small impairment of a single zone could have significant impact for your resources. And so we realized that the same outlier detection approach would work equally well to find impaired AZs. It's actually basically the same problem, but with a much lower cardinality. So Lambda also built a zonal event detector. It looks at different metrics to try to detect when an AZ must be unhealthy. And this allows Lambda to shift away from that zone and only invoke your functions in AZs that they actually observe to be healthy. So just like the Fleet Health service, Zonal Event Detector works so well that other services wanted to use it too. And so we wanted to build more and more capabilities that could use this telemetry to detect single AZ impairments. And so one of the things that we launched in 2022
is Zonal Shift. So Zonal Shift is an API that allows us to manually or automatically shift traffic away from a specified availability zone. Combined with Zonal Event Detector, we now have common signals and standard tools for all our service teams to be able to use to shift away from a zone. And we also put this capability in the hands of customers, so you can use this tool as well to shift away from a zone if you need to. And we now support all NLBs and ALBs, as well as auto-scaling groups and EKS clusters. So when you trigger a zonal shift, we inform both the DNS and load balancing layers, so traffic stops being sent from the outside to the AZ you shifted from. Auto-scaling sends all new instance scaling and replacements to the remaining zones, and EKS learns and removes endpoint slices and stops scheduling new pods in the impaired zone. For safety, we strictly limit shifts to one zone at a time. Again, we don't want to go over budget and take too much out. We also recognize that for customers, detecting a zonal event to use this tool was kind of difficult. So we saw another opportunity to shift more responsibility to our side. So we're in a position to look at a broader set of telemetry, including our infrastructural metrics, allowing us to better detect these events and respond more quickly on behalf of customers. So we use the Zonal Event Detector service that was born in AWS Lambda as a system-wide source of telemetry about AZ Health to power Zonal Autoshift. With Autoshift, we manage all of the observability and perform the shift on your behalf. So when one of our metrics, like connection failures or network reachability, show that one AZ is an outlier, the Zonal Event Detector goes into alarm, and we trigger a zonal shift. Again, we strictly limit this to one AZ at a time. And we use this capability for both AWS services and nowadays for customer applications as well. So this means that when you're interacting with a regional AWS service like SQS or Lambda, we're automatically responding to the event so that the AWS services recover quickly. But for resources that you enroll in Autoshift, we perform the same action at the same time. And this provides a single automated response driven by Zonal Event Detector and ensures we're all able to make best use of availability zones. So the second availability axiom was resilience to AZ impairments, and in particular to gray failures. And the axiom inspired the Lambda's Fleet Health Service, Zonal Event Detector, as well as Zonal Shift and Zonal Autoshift.
All right, the next axiom that we're going to look at is testing rigorously. At AWS, we commonly say, if you haven't tested something in the past week, it's broken. Regular testing is part of our operational culture. In order to use Zonal Shift, we also enroll you in practice mode. On a weekly basis, we perform an Autoshift to make sure all of our service teams and customers are ready and can actually perform a Zonal Shift without impact to their services and applications. We regularly do this in our production fleets, and it helps build the confidence that all of this is going to work when we need it. Just like a field goal kicker, they practice over and over, going through the same mechanics every time. And so when it's game day, nothing changes. They do the exact same thing that they've been practicing all along. Field goal kickers tend to make most of their extra points. In fact, it's a stat of something like 95% success. And that's because practice is so similar to the real thing. It's all muscle memory at that point. They have a high degree of confidence that they're going to make the kick because they did it over and over in practice. In my undergraduate degree, I was a philosophy major, and I never imagined that I'd be standing on a stage quoting philosophy, especially working in a technology company. But I think our mental model is captured really well by this quote. We are what we repeatedly do. Excellence, then, is not an act, but a habit. And while Will Durant and Aristotle were talking about ethics, I do think this way of thinking is equally applicable for so many different disciplines. By practicing over and over, we build up this idea of excellence. When the real thing happens, it's just muscle memory. So
one of the ways we do this internally at AWS is with game days. We want to know that our services are resilient to a variety of different failure modes. So individual teams will naturally test their service in pre-production environments. But when we build new AWS regions, before the regions go live, we take a couple of weeks out and we run a series of game day tests on the production services that are ready for customers but not yet serving customers. And this gives us an opportunity to test in real production environments at full scale without impacting any customers. We test a variety of things like power outages, network partitions, service failures, and these help us validate how services behave during failures, as well as how they recover afterward. They also provide an opportunity for our on-call engineers to train for real events, exercise and refine our runbooks, and ensure the required observability is in place. It helps validate our competence envelope. Professor David Woods at Ohio State University talks about socio-technical systems as having a competence envelope. This is an analogy with an aircraft's flight envelope, which defines the safe boundaries in which an aircraft can operate in terms of altitude and speed. And pilots know to stay within that envelope as it's the safe tested space. If they go outside it, things become more uncertain. And similarly, a competence envelope for a system is the space within which it is known to function competently or robustly. When pushed beyond its competence envelope, systems may still function, but things can become more prone to failure and we have uncertainty. And this competence envelope can be a useful mental model to think about test coverage. If you think about a system you own and all of the modes you expect it to be able to operate in, such as fallback paths or failures of hosts, failovers of hosts, when was the last time you tested all of those modes? Are you still confident that they are all still within your competence envelope, they're well tested?
And so we can take this idea of a competence envelope and generalize it to distributed systems as well. There's a set of inputs, parameters, and failure modes that our systems operate in with expected behavior. We're generally not near those competence envelope boundaries, so we're comfortable and safe. But as we start to move towards the edge of our competence envelope, and even beyond it, by being exposed to operating modes that we haven't seen before, we enter this danger zone, where our systems start to exhibit unexpected behavior to unknown conditions. In our case, it's not flying outside of a max altitude or top speed. It's dealing with failure modes that we haven't practiced with. This is where surprises happen and where danger occurs. So our competence envelope is defined by the failures we regularly test against. And while I'm showing our competence envelope, while I'm showing our operating mode expanding, it's also true that the competence envelope could be shrinking. If we're not regularly testing against these operating modes, we might not get the expected behavior that we want. And so how do we maintain or even expand that competence envelope? Well, in airplanes, you can't really change the characteristics of the flight envelope, right? With a plane, we're pretty much stuck with a max altitude and top speed that it has. But fortunately, in distributed systems, our ability to produce expected behavior is dynamic. By regularly testing and validating expected behavior, we can maintain the size of our competence envelope. And we can grow it by regularly exposing our services to a growing set of failure modes that we might encounter. We want fewer surprises. We want predictable behavior. And we do that by turning unknowns into knowns through constant testing. And so this is part of the test rigorously axiom. If we haven't tested it recently, it's broken. It won't work as expected. And we'll find ourselves in danger of not meeting our goals. So doing game days for individual teams in pre-production environments and our new region builds is a great start. But we only have so many new region builds going on at the same time, and there's a short window between when all of our services are ready and when we want to go GA and start onboarding customers. And so we want to do this type of testing with much greater velocity with all of our services in production environments.
So the results from those new region launch game days we were doing were actually really successful, so much so that we decided to make a more significant investment and build an AWS region dedicated to this kind of testing all the time. We wanted to be able to run game day tests in a safe space with no customers anytime we wanted, and not just in the run-up to a region launch. We finished building the test region with 3 AZs and a full complement of the AWS services earlier this year. To be clear, it won't be open to US customers because you don't want to be in that region, trust me. And it won't be on the health status dashboard. But we are all the time using it to improve the availability of the other regions. So the Gameday region helps us to further expand our understanding of how the systems will function in rare conditions. The idea is that service teams all treat the Gameday region as just another production region, but one that just doesn't happen to have any customers in it. This allows us to continuously propose and schedule game days without waiting for the next region to launch. So what are the kinds of things we test? There's a standard sort of set of benchmark tests that are important to us, like we'll power down an availability zone or disconnect it from the network. We'll break a common dependency service to validate services are resilient to that. We'll perform a cold start of a service and see that everything recovers as expected. And then some less common things like if we have an event and we make a correction to a system to fix it, we will actually recreate the event in the test region in order to validate that the fixes actually work. We also create some novel rare events where we kind of sit down and kind of brainstorm and come up with things that we've never seen, but we would like to validate what will happen. Will we recover from that kind of event? So the third axiom focused on rigorous testing. And this has inspired not only a set of high standards in terms of continuous integration and deployment, but also the concept of running region-wide game days with all services and building a dedicated region ultimately for that purpose.
Our final axiom is about protecting against overload. Overload is one of the most common sources of impact that we see. And while we have a number of protection mechanisms, like load shedding, rate limiting, adaptive retry strategies, and more, there is a type of overload situation that is quite rare, but can be really impactful. We've seen it occur in our services, and it's something that we like to prevent. And what I'm talking about are metastable failures. At a high level, metastable failures look like this. First, the system starts in a stable state where everything's good. But then over some period of time, load increases, and we enter this vulnerable state. The system's still healthy, it's not overloaded yet, and it could operate this way for months or even years. In fact, many systems intentionally choose to operate in this vulnerable state. But what happens is, at some point, there's a trigger. And this trigger creates a condition where the combination of the existing load combined with some spike, either through retries or some other source, transitions the system into the metastable state. In the metastable state, a feedback loop sustains the overload and keeps the system in a stable down state, and it doesn't recover. The system remains in this state until a big enough corrective action is applied, typically done manually by an operator. And so if that seems very esoteric or high level, let's look at a concrete example where we've seen metastable failures occur. We see these commonly happen in queues. And it's important to note that queues are all around us. They may be embedded in libraries that you use, or part of how networking equipment manages moving packets around the network. So lots of possible places where a queue could exist in your system, even if you're not using one directly, like an SQS queue. So under normal conditions, our server here can process the messages in the queue, and the queue depth stays manageable. It doesn't grow beyond what the system can successfully process. But when there's a sudden load spike, right, in this case that's the trigger event, the queue depth grows. The server continues to process messages, right? It's unaware that the load spike happened, but as it's working its way through the backlog, it can't get through them all. Eventually, the messages in the queue get older and older. And then new requests come in. And now the things that were waiting on those messages to be processed have given up, like a TCP client. They've stopped waiting. And so we start to have wasted work. we're doing work on messages that have no chance of success. And because we're processing first in, first out, we're always working on the oldest messages in the queue. And so those clients that got tired of waiting, well, they retry their requests. And that continues to add to the queue depth. And so the combination of our steady state requests and the work amplification of the retries have created the sustaining effect. The queue depth is insurmountable. We have more wasted work. And so even after this load spike is removed, the system can't recover. It's doing lots of work, just none of it's useful.
So we've seen this pattern across the industry of these metastable failures. And they can lie dormant in systems for a long time, especially systems with queues. And as metastable failures by their nature have long recovery times and happen rarely, they are a high priority for us to find and prevent. So we brought together a group of scientists within AWS to study them deeply and ask, how do we efficiently find these systems that might have these risks so we can test and fix proactively? And one of the big challenges with so many services and microservices is how would you figure that out? Where would you start? How do we figure out which systems to look at? And direct testing of an individual system is pretty expensive, so we have to be able to figure out where are the places to look. The problem is that the parameter space is really large even for one system. You have different queue lengths that might be problematic. You have different retry rates. The parameter space is huge. So the scientists built a multi-step strategy to efficiently search this parameter space and map out where it is we should focus our testing. And this consists of a statistical model that can quickly explore the full space for a given service on just running on a laptop, a simulation that can also run on a laptop and actually run services that talk to each other in a simulation mode, again on a laptop. And then an emulation, which is on physical servers, but just running dummy code where they'll sleep instead of doing actual work, but which can cheaply imitate the important characteristics of the service. And then finally, once we've narrowed things down and figured out where we're concerned about, we can actually approach the teams and run the real test and build the system, scale it up out of production to do the tests. And this strategy has saved us a huge amount of time and energy. So for the statistical modeling piece, the team built and open sourced a tool called Metaphor, which you can get on GitHub. This performs the calculations and creates these visualizations. It's a really lightweight way to begin understanding where a metastable failure might occur in your system. So in this visualization, you can see the queue length on the x-axis and the number of outstanding retries on the y-axis. So each point on the graph represents a point in the state space, and the arrows visualize the most probable transition in the next time window. So where you see the arrows moving to the left, we're probably draining the queue. Where you see the arrows moving to the right, we're probably growing the queue. And so you can see there's this inflection point line on there for this system, and this allows you to visualize that quickly. The team released a paper recently with the details of this research and presented it at HotOS 25. If you'd like more details, the research paper and the GitHub link are there as QR codes. So our fourth and final axiom for today was for our services to protect themselves against overload. And this axiom inspired us to do a lot of work, but including funding this work on tipping point and metastable failures.
So today we've taken a look at some of the behind-the-scenes work where AWS is innovating on your behalf in areas that might not be completely obvious to you as customers. We help migrate almost all of the existing global STS traffic transparently to be served in each region locally, helping strengthen the regional isolation of customer workloads. We built a fleet health service and zonal event detector that powers zonal Autoshift, allowing AWS services and customers to detect and respond quickly to single AZ impairments. We built the AWS test region so that we can run game day activities all of the time, accelerating our ability to continuously validate expected behavior in our services and to continue to expand our competence envelope for new operating modes. Finally, we're actively pursuing research on metastable failures to help protect our services against rare but really impactful scenarios that create overload conditions. We're always looking for ways to innovate that transparently improves the resilience of the cloud and reduces the burden for customers to achieve your resilience goals. Our obsession with resilience and our culture of innovation makes AWS the best place to run mission-critical workloads. Thank you all so much for coming today. Please remember to fill out your surveys and have a great rest of your Reinforce. Thank you so much.